It's my pleasure tonight to say that we have, to speak to us about the great astrophysicist Georges Lemaître, another astrophysicist of distinction in his own right, Jonathan Lunine. Jonathan is the David C. Duncan Professor in the Physical Sciences at Cornell University, the Director of the Cornell Centre for Astrophysics and Planetary Science, and Vice President of the Society of Catholic Scientists, an organisation that was founded with the assistance of the Lumen Christi Institute. Professor Lunine's work, or research rather, concerns how planets form and evolve, and what kinds of processes and environments can host and sustain that remarkable thing that we call life. Now, I think it's worth noting, especially at a time when, after a rather long hiatus, the future of humanity's relation to outer space is again perhaps on the table, or at least in the public eye once more, that Professor Lunine has pursued these interests not only through theoretical modelling, but also through participation in spacecraft missions, including in missions that have become legendary in the astrophysical community and even beyond it, such as Voyager 2. The stuff of childhood dreams indeed, albeit he hasn't actually been up there himself yet, I take it. No. Not yet, at any rate. So one childhood dream at least yet to be fulfilled. The fact that Professor Lunine is a participant in spacecraft missions is one of several facts that makes me feel a kind of affinity as well as admiration for him. Another is that he cites University of Chicago product Carl Sagan as an early influence and tells a wonderful story about how, having at the age of 13 or 14 been reading a book of Sagan's out loud in the house, something I may have done myself at the same age, I think, his mother finally pushed him to write to Sagan, who replied at some length. They entered into a correspondence, and later the two of them worked together on Cassini, the famous collaborative mission to Saturn. A wonderful story, and one that confirms, I'm glad to say, my boyish impression of Sagan, formed as it was from reading his books, and no doubt incomplete. I won't say anything about Professor Lunine's philosophical or spiritual development, which in some, if not in all ways, appears to have taken him rather far from Sagan, though he has discussed it himself for publications like the Catholic Courier. Perhaps he will say something about it in the context of Lemaître, who was, after all, a priest, but if not, there is some material on the public record for those curious about this aspect of his life. So now, please welcome Professor Jonathan Lunine.
Thank you, Jack, and thanks to the Lumen Christi Institute for having me here, and also for, as you pointed out, supporting both the formation of the Society of Catholic Scientists and our first meeting, which was held here in Chicago about a little more than a year or so ago. I have been concerned for a long time, as I think many of you have, about the rupture between science and faith that we witness in our society. And it's a rupture really in which individuals regard their, particularly young people, regard their pursuit of the profession of science as somehow inconsistent with the maintenance of their faith. Or their colleagues, their friends will say the same thing. And so I think it's very important that we identify role models, not only living role models, but historic role models that contradict the hypothesis or falsify the hypothesis that science and faith are incompatible with each other. And Georges Lemaître is an outstanding example of somebody who lived both aspects of his life harmoniously, even when he was challenged on both ends. For a long time, Lemaître was forgotten by the astrophysical community. And beginning about 10 years ago, he was rediscovered through the efforts of several astronomers who you'll hear about, culminating ultimately in a vote by the International Astronomical Union, which is a union of an international union of scientists, astronomers, to attach his name to what has been known as the Hubble Law. And I want to describe for you this evening why that change makes sense. And I also want to describe some of Lemaître's experience in his life as a Catholic priest as well as an astronomer, really a cosmologist. And I'll talk a little bit about some of the theological and philosophical aspects of the insights that he brought to astronomy about the beginnings of the universe and the fact that the universe had a beginning that was very different from what we perceive as reality, our life in the cosmos today. So that's a tall order for 45 minutes, but I'm going to do the best I can. Georges-Henri Lemaître, and that is the last time I will attempt the French pronunciation, was born in 1894 in Charleroi, Belgium. He served with distinction in the artillery in the 3rd Army Division in Belgium in World War I. In fact, he argued the only reason he didn't become an officer was that he made the mistake of pointing out an error in the artillery manual to an officer, which led to a punishment, of course. It was a physics error. But he was decorated nonetheless. He went on after the war to obtain both degrees in mathematics and physics, as well as to be ordained as a Catholic priest. And he knew from his childhood that he wanted to do both of these things. His PhD in physics from MIT was actually work that he did at the Harvard College Observatory on variable stars. Harvard College Observatory did not award PhDs at that time. I believe they award PhDs now. I think that's correct. That joke goes over much better in Ithaca at Cornell, believe me. So, and he got his PhD at MIT. He then went back to Belgium, to Leuven, where he became a professor, and he spent his entire academic life at the University of Leuven. But what's important to note is that the period after he was ordained in 1923, up to the time that he went back to Belgium, he traveled to England and worked with Eddington, who was a prominent cosmologist. Of course, he worked in the United States. He interacted with Einstein, and he also interacted with Robert Millikan, a physicist at Caltech. And through these interactions, he formed ideas that would lead ultimately to the concept that we call today the Big Bang model for the origin of the cosmos. There was no internet at the time. Interactions between scientists had to be on a personal level. Journals were delivered after weeks or longer. And so it was a very different kind of interaction than we're used to scientifically today. He was nominated by Einstein for the Franke Prize in 1934, which he won. That was, at the time, the second most lucrative prize in science after the Nobel. He won the Eddington Medal in 1953 from the Royal Astronomical Society. He was elected to the Pontifical Academy of Sciences in 1936. He became its president in 1960. He went emeritus in 1964 and died 2 years later. Now, this outline of his life, although it looks impressive, doesn't really give you a flavor for what he did and how he did it. And so that's what I want to do now. So I'm going to start with Lemaître's contributions to general relativity and the concept that the universe is expanding. And it's through that he, in fact, contributed much more to our understanding of cosmology than up till now has been acknowledged. And so we'll get into the question of the Hubble Law and the expanding universe. So we celebrated the 100th anniversary of general relativity last year. And at the time that Einstein developed this theory, which was a theory of gravity, which was essentially geometric in nature, the going assumption was that the universe, everything, all matter, us, stars, etc., were static. It was an eternal, unchanging reality. Part of this was philosophical, and part of it was that there was no evidence that things were changing. In fact, what we call galaxies today, such as the Andromeda Galaxy, which you see in an old photo from a little bit after that time, were really not known to be objects outside our own Milky Way galaxy. One perfectly acceptable model of the cosmos was that the Milky Way galaxy was all there was, and that these other things that we recognize today as other galaxies were simply agglomerations of gas that were called nebulae, a Latin term for cloud. So when Einstein developed his theory, his bias was that he was describing the effects of matter on an unchanging universe, an unchanging space-time construct. And so, of course, he recognized when he developed this model that because matter distorts space, and that's the essence of general relativity, that the agglomeration of matter in the cosmos would by itself cause everything to collapse in. All of space would collapse in on itself, and we shouldn't be here. And so to fix that, he introduced into his theory a fudge factor called the cosmological constant, which was essentially a repulsive term that would counteract gravity. And he published that and regarded that later on as a great mistake. And the reason he regarded it as a great mistake was that he hadn't accounted for the possibility that the universe, space, and the matter within it could all be in motion in some way. And in fact, only 5 years after 1917, after the publication of the model by Einstein, a Russian mathematician by the name of Alexander Friedmann explored a range of possible universe models in the context of the theory of general relativity, one of which was an expanding universe model with matter in it. And in that model, he showed that the equations, that the theory of general relativity could be applied to a universe that was expanding and would do so, therefore, without effectively the aid of a cosmological constant. Now, he didn't identify the source of the expansion. He didn't have any data to apply to this. He was in the Russia of 1922. In fact, Lemaître didn't know of his work. Very few people did, except for Einstein. And Friedmann died very young. He died a few years later and was never part of the conversation about the cosmology of the cosmos, of the universe, after that. Now, around the same time, another cosmologist, de Sitter, published a solution to the equations of general relativity, which was very different. Space was static, but it was also empty. There was no matter in it. And by doing that, he showed that without a cosmological constant, the universe wouldn't collapse on itself. Now, that would seem a little bit artificial, not to have any matter in the universe, but it was a useful model because, in fact, the way the geometry of that model worked is if you put two test particles in this empty universe, they would actually begin to move away from each other. And so it was a model which suggested that you might actually see galaxies moving away from each other, although it was not a realistic depiction of our cosmos as we know it today. It might well be in the very far, far future when the universe becomes very dilute. So that was the environment within which Lemaître began to work. And he, in his PhD thesis and the work immediately after, what he did was to take the de Sitter model, which actually had a number of advantages. These models involve describing a metric, which is kind of a matrix of the way mass interacts with space-time. He used the de Sitter metric, but he modified it so that you could have matter in that cosmos. And furthermore, he did what Friedmann had done, but without knowing it. He allowed space-time itself to expand. And that was a solution that worked. But what Lemaître did that neither de Sitter nor Friedmann nor in fact Einstein did was that Lemaître, having worked on his PhD thesis on astronomical data, actually compared that model to the data that were available in that time period, which is now the mid-1920s, so 10 years after Einstein. By that point in time, observational astronomers had done two things. They had determined once and for all that these nebulae were actually other galaxies that were beyond our galaxy, and the universe was far larger than had been previously imagined. And in fact, that was something that Edwin Hubble contributed to very much. I'll get to that in a few minutes. The other thing that astronomers had discovered was that the galaxies did indeed seem to be moving away from each other, on average. Some of the closer ones, not so much, but the more distant ones were. And that was work by an American astronomer, among others, but I want to call him out because he is one of the best names that I can imagine an astronomer could have, Vesto Slipher, who worked in Arizona. And so he did a lot of that work. Now, as I'll describe, Lemaître's solution to general relativity specifically implied that there was a proportionality between the distance to the galaxies and the speed at which they were moving away from each other. And I'll get back to that in a minute. But first I want to talk about, very briefly, how distance and speed are actually found in astronomy. And if I were to do this properly, we would be here for a few classes. So I'm not going to do this in any but a very cursory way. Distances in the cosmos are determined by bootstrapping one technique after another, starting with techniques that give you the distances to the nearest stars. This is in particular parallax, or the apparent shift of nearby stars against the background. And then using that distance information to, with a different technique, extend the distance scale further. So you basically link different techniques to eventually get what's called the cosmic distance ladder. Now, what Hubble contributed, among other things, was a study of what were called Cepheid variable stars that have this peculiar property that their absolute brightness is related very simply to the period with which they pulsate. And so what that means is that no matter how far a Cepheid variable is away from you, so you don't really know its intrinsic brightness, you can find that brightness by measuring the period of the pulsation. And once you have the absolute brightness, you compare that to the relative brightness, you now have the distance. That technique was what Hubble used to determine distances to galaxies with a colleague, Milton Humason. It's also the technique used with the Hubble Space Telescope that helped to refine distances and determine that our universe is not only expanding, but is actually accelerating. Cepheid variables and supernovas. Of course, that's many decades later. Now, the distances to galaxies is one thing. The recession speed is another. And this is determined by measuring the colors of galaxies, or their spectra, as you see on the right-hand side of this slide. And as very much is the case with a train whistle, for example, if a galaxy is approaching you, the light of that galaxy is shifted to the blue, just as the pitch of a train whistle or a car horn is shifted toward higher pitch. If it's moving away from you, then the pitch gets lower, if we're talking about a train whistle, or the wavelength of light gets longer, the frequency gets lower, and so the galaxy appears redder. This is sometimes called a Doppler shift, and it's easy to use with galaxies because galaxies have very recognizable signatures in their spectra. And it was from that it was determined by Slipher and other astronomers that on average galaxies are moving away from each other. Now there's an ambiguity in this, which is, are the galaxies moving away from each other in a fixed universe, or is something else happening? What Lemaître realized, as well as a few others, but many other astronomers did not, was that in fact this red shift that was seen was the result of the expansion of space itself. So to illustrate that, because this is a big lecture hall, I didn't bring my balloon, I photographed the balloon. I can draw a squiggle, as you see on the left-hand side, of light coming from a galaxy close to my thumb and traveling to the observer, which is the dot in the middle. And what I'm imagining here is to take the 3 dimensions of space that we exist in and collapse them to the 2 dimensions on the surface of the balloon. So the balloon surface is the cosmos, okay? Now, space is curved, but the curvature of space is very, very small in the real world. It's like having a balloon so large that you can't notice that it's curved. But we're not going to worry about that for the moment. So this light takes a finite amount of time to travel to the observer, and during that time, the balloon is inflated. So I've put air into the balloon, and now it's bigger. And so by the time the light reaches the observer, the wavelength of light, which is the blue bar on the left, has become the red bar on the right. And if I compare the sizes of those two, you see that the red bar is longer. The wavelength has become larger. The light from that galaxy appears redder because space itself is expanding. And in that situation, with the metric that Lemaître had applied to the equations of general relativity, the distance to that galaxy is just proportional to the recessional velocity. The larger the distance, the higher the recession velocity. Now, the canonical story in astronomy is that this was discovered by Edwin Hubble. And indeed, he discovered it through the observations. By the time he published his paper, which first explained Hubble's law in 1929 in the Proceedings of the National Academy of Sciences, there were enough data on galaxy distances and velocities that he could actually show from the data this linear relationship, with which I've written here. The recession speed of the galaxy is equal to the galaxy distance times a simple constant of proportionality, which eventually came to be known as Hubble's constant, and that equation became known as Hubble's law. And the Hubble constant is a velocity per distance. It's usually given in kilometers per second per megaparsec. Now, a parsec is a unit of distance in astronomy. Let's just take that as a unit of distance without having to worry about how it's derived. A megaparsec is 1,000,000 parsecs. And in those numbers, the value that he derived in that day was something like 540 kilometers per second per megaparsec. And so this is what Hubble is credited with, and he deserves to be credited with it. But Lemaître published this same relationship 2 years before Hubble did. He published it not in English in the Proceedings of the U.S. National Academy of Sciences, where Hubble published. Lemaître published this in French in the Annals of the Scientific Society of Brussels, a journal that probably no American or British astronomers ever read. And by that point, astronomy was dominated by the Germans and the Americans and the British. And so in this paper in 1977, Lemaître presents his solution, which is a modified de Sitter universe expanding with matter in it, and he shows that that implies a linear relationship, and he then actually goes on to derive what we call the Hubble constant. But no one paid attention to this, nobody knew about it. And so as the astrophysicist Robert Kirchner pointed out, Lemaître was just underrated. He wrote in French, whereas English was really the lingua franca of astronomy by that point, and he published in an obscure journal. But then the story takes an unexpected turn. Lemaître had worked with the famous cosmologist Arthur Eddington when he just after he became ordained, before he went to the U.S. And they had continued a correspondence. In 1930, 3 years after Lemaître published his article, which he had sent to Eddington, but it was in French, Eddington presented a paper at a conference with his own solution to the equations of general relativity, which looked remarkably like Lemaître's, and which he said he had thought up. A colleague of Lemaître pointed out to Lemaître, who was not at the meeting, that this had happened. Lemaître wrote to his former advisor politely. It was actually, in fact, published in this magazine, The Observatory. And Lemaître pointed out that he had actually come up with this solution several years before. Now, those of us who are astronomers know that we sometimes have colleagues who, if we were to do that to them, they would write back in a rude way saying, well, yeah, but you didn't do this and that, I thought it up first. Eddington did not do that. Eddington, who by the way was a devout Quaker, was mortified, realized that in fact Lemaître had talked to him about this solution. He had forgotten this, as we often do, and had rethought it up himself. So he responded to Lemaître and said, we need to get that paper published in an English journal. And so Eddington contacted the editor of the monthly notices of the Royal Astronomical Society, a prominent journal, and had the English language translation of Lemaître's 1927 paper published in 1931. So then Lemaître would get credit. However, the key portion of the 1927 paper in French that described what we call the Hubble's Law was missing from the 1931 English version in the monthly notices. And that key phrase is here, and nowadays it takes 30 seconds to get this paper off the internet. Okay, back in those days, a little different. So anyway, what it says in French, this is Lemaître's work, using the 42 galaxies taken from Hubble's list and from Stromberg, who was another observer, and taking account of the proper motion of the sun, which biases everything, which was 300 kilometers per second in a given direction, one finds a mean distance of 0.95 million parsecs and a radial velocity of 600 kilometers per second, that's the recession velocity, and therefore 625 kilometers per second per million parsecs. And Lemaître had derived the Hubble constant and the Hubble law before Hubble did. Now, there's a caveat to this. Lemaître had plotted the data that he was using and realized that it didn't actually fit a straight line very well, but he knew it had to be a straight line from his model. And so he realized he couldn't show that, and so what he actually did was, knowing that this must be a linear relationship, he just took the mean value, and he took the mean value of the velocity and divided it by the distance. So he didn't demonstrate from the data that this linear relationship existed. He knew it had to exist from his model, and he derived the proportionality constant. Hubble, on the other hand, 2 years later, with better data, was able to show that it was actually a linear relationship between the recession speed of the galaxies and their distance. So both contributed in different ways. Now, the omission of this part of the French paper up until 2011 was unexplained except by conspiracy theorists, not UFO conspiracy theorists, but this was some anti-religious thing. But it wasn't. Mario Livio, a scientist at Space Telescope, actually unearthed in the files of the Royal Astronomical Society material that showed that the omission was actually made by Lemaître himself. And in a letter that Lemaître wrote, a cover letter, along with the English translation of his paper to the editor of MinRAS, Lemaître says that he sends the translation of the paper, which he did himself. He said, I didn't find it advisable to reprint the provisional discussion of radial velocity, that's the recession velocity, which is clearly of no current interest. He used a different word, which is sort of a false friend between French and English. His English wasn't perfect, but it's clear that he meant of no interest in that year, on that day. And then he said, I made the translation as exact as I can. So it's clear that Lemaître, having seen Hubble's paper, realizing that what he had in 1927 in terms of data was much sparser, didn't see any point in including the part of the paper that he regarded now as out of date. But by doing that, he lost the priority on that law. So the irony in all of this in the end is that as great a scientist as Edwin Hubble was, and I recognize he was a graduate of this institution, he never really understood general relativity, and he never accepted the idea that the universe was expanding. In fact, his explanation for the redshift, what we call the cosmological redshift, was something called light fatigue, where as light traveled farther and farther, it just lost energy and got redder. In 1941, in an interview in the Los Angeles Times, which is shown here on the lower left, he says straight out that the data don't support an expanding universe. Einstein came and visited him at the Mount Wilson Observatory. He was a guest of Hubble, and he looked through the telescope, but he was also there to try to convince Hubble that, the universe was really expanding. Hubble didn't accept that. Now, that doesn't take credit away from Hubble for the Hubble Law, but it does mean that anyone who argues that Hubble essentially discovered the expansion of the universe is not quite right, because that's not the interpretation that Hubble gave to these data. Now, the American Institute of Physics, or American Physical Society, in its biography of Hubble, tries to sort of make a little euphemism about this by saying, well, Hubble preferred to leave the interpretation to the theorists, but it was actually more than that. So, good, it was blank on my screen. That was not the end of Lemaître's contributions. Lemaître, having published this metric, this solution to general relativity, thought about the implications of this model, and he knew that what this meant was that if you ran the tape backwards on his cosmos, space and time, space would get smaller and smaller, matter density would go up. Eventually you'd get to something extremely small, extremely compact, and in his view, this was the equivalent of a kind of a single atom, and from that point you could go no further, and so the universe had to have a beginning. And so in 1931, Lemaître published, this time in an English language journal, Nature, a letter entitled "The Beginning of the World from the Point of View of Quantum Theory." And he lays out an idea for the starting conditions, the idea that this primeval atom, as he called it, would fragment and space would begin to expand and time would begin. And this was effectively what we call today the Big Bang Theory, which was not a name that he put to it. I'll tell you in a few minutes who put the name Big Bang to this primeval atom model. You know who it was. Stephen Hawking, who was somewhat skeptical of some of Lemaître's contributions, straight out gives credit to Lemaître for the Big Bang model. Now, all of this would be fine, and Lemaître continued to tour and give talks, but there was always the issue with respect to some other astronomers that somehow this primeval atom model had a religious origin to it. A lot of astronomers just didn't like the idea that the universe had a beginning, because if it had a beginning, what was there before that beginning? It just smacked of some kind of religious philosophy or undertone to it. And Lemaître always denied that. And I'm now going to talk about an episode in Lemaître's life which made it harder for him to deny that. And of course, fiat lux, let there be light. The astronomers who in particular didn't like this model so much that they invented an interesting alternative model were Sir Fred Hoyle, a very famous British astronomer and a great popularizer of science. He had his own BBC radio show. You see him over on the right side, rolling up his sleeves. Hermann Bondi in the middle, and Thomas Gould, often goes by Tommy Gould, from Austria. And they developed a model in which the universe was eternal and unchanging, but it was expanding. Now, how could it do that? If it's expanding, it becomes more dilute. Well, what they postulated was that matter was continuously being created. It didn't have to be very much. It's something like a hydrogen atom per cubic centimeter every few billion years or so. Okay, you'd never notice it. It's like I never noticed my hair disappearing back here or reappearing. And it worked. I mean, it was fine. Everything that was known in the 1940s, that model worked just as well. And the delay between the 30s and the 40s was really the effects of World War II in Europe that really put a damper on science from the late 30s to the mid-40s. Now, there is a Cornell connection with Tommy Gould, the man on the left side, he went on to found the Center for Radiophysics and Space Research at Cornell, which I direct today. He was a brilliant scientist, often wrong and often right. In this case, the three of them were wrong. But Hoyle was a great promoter. And in fact, on his BBC radio show, he asserted that the genesis, no pun intended, of the Big Bang model was religiously motivated. He didn't directly refer to Lemaître, but he was referring to Lemaître. And in fact, Hoyle would sort of sarcastically refer to this exploding universe model as the Big Bang. He was the one who put that term to the model. And he didn't do it from a complementary point of view. So Lemaître insisted, on the other hand, that his model had no religious implication. You could be an atheist, you could be a believer. Either way, it had no implication for the model or accepting the model whatsoever. So, of course, who's the guy to ruin this all but the Pope, right? So Pope Pius XII was a very intelligent man. He was a bright scholar who really enjoyed digging into the science and technology of the day. And he would read voraciously, and he would learn the language of that science. And in this case, again, after World War II, he was invited, wasn't invited, he gave a talk to the Pontifical Academy of Sciences, which was his academy. And this talk is referred to as the Fiat Lux talk, because in it he basically said that astronomers, he didn't call out Lemaître specifically, that astronomers had discovered that the universe had a definite beginning. He describes with this brilliant prose the formation and expansion of galaxies, and he says, this proves that there was a creator. Well, Lemaître was horrified at this for two reasons. One is the Holy Father didn't mention his name. He pointed out to a student that that was irritating. But the other was his model, which he asserted was not connected with any sort of theology, was now directly connected with the book of Genesis by the Pope. And furthermore, he learned that the Pope was invited to give the opening address to the International Astronomical Union the next year in Rome, which was a much, much larger group of astronomers. So Lemaître actually visited Rome on his way to South Africa and intervened and was able to talk down the Pope. It's not clear whether it was directly or through the director of the Vatican Observatory was there as well, convinced the Pope to not give that speech, which the Pope, to his credit, never did. He never mentioned this anymore. But the damage was done, and so there was always this suspicion about that model. Now, Lemaître was not active in this field in the 40s and 50s, and I'll get to why that, or the 60s. He did other things in science, had students doing other sorts of problems. And I'll talk about why that is at the end of the lecture. But at the time of his death, the first direct evidence that the Big Bang model was correct and the steady state model was wrong came through observations with a radio telescope by two Bell Labs engineers, Penzias and Wilson. Now, in Lemaître's model, he envisioned this primordial atom at the beginning as breaking apart, and the signature of that he thought were cosmic rays, which he had learned about from Millikan at Caltech. That was wrong. That was a cold start to the universe. A hot start to the universe involved temperatures so high that the matter in the universe in the early period, for about 400,000 years, would absorb all the light immediately around it. So the universe would be opaque. As the universe expanded and became more dilute and cooler, there would come a point when the universe was no longer opaque. It was transparent. Light could move freely. That surface in time, when it's redshifted out by the expansion of the cosmos, looks like a almost uniform microwave signal. And that's what the Bell Lab engineers detected. And at that point, it was clear the steady state model, which had no provision for this, was wrong. Very close to his death, Lemaître was following these results, and he was talking with some colleagues at least a few days before his death, maybe a bit before. But I think it's a wonderful thing that he was able at the end of his life to actually find out that his model was right. Now, I want to shift gears, and I guess I have to end at 8 o'clock, so I'm going to try to end as close to that as possible so we can have questions. I want to shift gears to the issue of conflating science with philosophy and theology. And this is something that I think contributes to the issue of difficulty of students who are pursuing science, who want to maintain their beliefs. There's this interesting quote from a book, The Grand Design, by Stephen Hawking and another physicist called Mladenov, in which, and I'll just read it straight out, they say, "What is the nature of reality? Where did all this come from? Did the universe need a creator? Traditionally, these are questions for philosophy, but philosophy is dead. It's dead," say the astrophysicists. "Scientists have become the bearers of the torch of discovery in our quest for knowledge." That's a very bold statement to make, but it's a statement I would venture to say most people believe today, including most science journalists. And if you ever take the unpleasant task of reading what you see on the web, you find out that that's really the case. And furthermore, scientists are believed far more often, if you read in polls, than people in most other fields, of course, more than politicians. So what a scientist says really matters, and scientists have to be careful about what they say. And for example, we know that Stephen Hawking has said that we know how the universe began from nothing, and that proves that there isn't a God. And I want to go through that argument with you to show that in fact those two statements, that the universe had a beginning and there is no God, are completely separate from each other, despite what Hawking says. So let's begin with the paper from 1931, which is the primeval atom model, in which Lemaître, who wrote this paper, says if the world began with a single quantum, a single atom, the notions of space and time would altogether fail to have any meaning. They would only begin to have a sensible meaning when the original quantum or atom had been divided into a sufficient number of quanta. So if there's only one thing that is reality, and that thing doesn't have anything to interact with, then there is no time, effectively. Nothing has happened. And then he goes on to say, therefore, the beginning of the world happened a little before the beginning of space and time. These are really interesting statements, because if you go back to St. Augustine in the City of God, from 1500 years before, he says exactly the same thing. He says, if eternity and time are rightly distinguished by the fact that time doesn't exist without some movement and transition, while in eternity there is no change, who does not see that there could have been no time had not some creature, read primeval atom, been made by which some motion could give birth to change, read it splitting up. And then he goes on to write, then assuredly the world was made not in time, but simultaneously with time. This must have been in Lemaître's mind when he wrote this, because the statements are so identical. But what's more interesting is that Hawking says exactly the same thing. In writings that were collected posthumously in a book, Brief Answers to Big Questions, Hawking says, and here he's paraphrased in another article, because the universe also began as a singularity, this primeval atom, but updated now, time itself could not have existed before the Big Bang. There was no time before the Big Bang. But then Hawking goes on to draw a conclusion from this, which is we have finally found something that doesn't have a cause because there was no time for a cause to exist in. For me, this means there's no possibility of a creator because there's no time for a creator to have existed in. So evidently philosophy is not dead because Stephen Hawking is doing philosophy. And he's doing it on exactly the same statement that St. Augustine and Lemaître did 1,500 years apart, and they surely were not arguing for the lack of a creator. In fact, the mistake that Hawking is making is he's conflating a creator of all reality with some kind of demiurge that exists in the universe and is just more powerful than we are, and he can't do anything because time hasn't started yet. Well, that's, Lemaître was confronted with that in various conferences, and he would often say, well, that's not the God that I believe in. And of course, many of us say that as well. And it's clear that Lemaître not only believed in God, but he believed, he was a priest, he believed that God was manifest through the physics, that God was hidden in the physics, but that his actions were in fact made through physics, and he went so far as to write that in his manuscript to Nature. So in the archives at Leuven, you can find this version of that article with the last paragraph that says that I think everyone who believes in a supreme being supporting every being and every action, that was a mistake on his part, acting, believes also that God is essentially hidden and may be seen to see how present physics provides a veil hiding the creation. So the Creator, in a Thomistic way, has brought everything into reality, and I'll give you a quote in a minute, not at the beginning, but is hidden in the physics that keeps everything going all the time. And so here is that quote. Lemaître distinguishes a beginning of the universe from the creation of reality. He says we may speak of this event as a beginning, I don't say a creation. Physically, it's a beginning in the sense that if something happened before, it has no observable influence on the behavior of the universe. Now, he did explore Phoenix universes where there were cycles in these Big Bangs. But the simple model is that all the information prior, if there was a prior, is simply lost. Any pre-existence of the universe has a metaphysical character. Physically, everything happens as if the theoretical zero were really a beginning. The question, if it was really a beginning or rather a creation of something from absolutely nothing, something starting from nothing, is a philosophical question which cannot be settled by physical or astronomical considerations. And that, I think, is absolutely correct, because the issue of existence, of being, is separate from the question of how the expansion of the universe began. Now, what's interesting as well is this idea of something coming from nothing as being an example of, or a proof of the non-existence of God, which also comes from another astrophysicist, Larry Krauss, can be turned two ways. On the one hand, Hawking says, the universe itself and all its mind-boggling vastness and complexity could simply have popped into existence without violating the known laws of nature. But on the other hand, if you're a member of the Soviet Politburo and also an atheist, admittedly from decades before, you don't like something from nothing. Zhdanov, who's an interesting case of Soviet ideology, says the reactionary scientists, Lemaître, Milne, and others, made use of the redshift in order to strengthen religious views on the structure of the universe. Falsifiers of science want to revive the fairy tale of the origin of the world from nothing. So it's very clear that how you regard the question of something coming from nothing is a philosophical issue. You can be a Soviet ideologue and believe that it is a false ideology. You can be an astrophysicist who doesn't believe in God and believe that something from nothing demonstrates that God doesn't exist. You can be a believing scientist and argue that the beginning of the universe doesn't tell you anything about the existence of God or not, because that's not the creation of being and beingness from a state of non-beingness. And that was Lemaître's point of view, and I think it's the more sophisticated of any of these points of view. I'm going to skip Lemaître's contributions to the vacuum energy because it's interesting but somewhat peripheral to what we're talking about here. I can talk about it in the question period. But I do want to point out that Lemaître's contributions to cosmology go beyond his solution to the equations of general relativity, the first exposition of what came known as Hubble's law, and the Big Bang. There's a laundry list of things he looked at during this period, actually out beyond 1934 to World War II. He talked, for example, about Phoenix universes, which we would call now cyclic cosmology, Big Bang collapse, Big Bang collapse. He did, in fact, identify the cosmological constant with what he called a vacuum energy, which today we would call dark energy. And in fact, a number of physicists, Alan Guth and Kirchner, have remarked on how modern that view is from the 1930s. But Lemaître was largely forgotten after the period in the 1930s that he played a key role. And if you read astronomy textbooks from the 70s, you hardly see his name. In fact, even this metric that he's recognized for with several other people, he's sometimes omitted from that. Kirchner's explanation for that, in an article in Physics Today, is that Lemaître, his contributions were undervalued, and he was a significant player in the formative years of relativistic cosmology. But he was undervalued not out of ignorance or linguistic bias, but because by the mid-1930s he stopped doing original research in cosmology and devoted himself to other aspects of academic life and to matters of faith. That actually is not true. For all the good that Bob Kirchner has done with this, if you look in the literature, Lemaître still was publishing papers and going to conferences. But what really stopped his work in this field was that he could not escape Belgium before the Nazis invaded. In fact, if he had left with his family about 3 days before, he would have escaped. And so he was forced to stay in Leuven. He was out of contact with the rest of the community. His university was actually bombed by the Allies by mistake, and several of the buildings that he worked in were destroyed, and he was nearly killed because his apartment was nearby. And so by the time World War II was over, he was really out of touch with the community. He had not been able to interact. And what had happened to the cosmology community was that they had moved from general relativity, which really kind of became a sort of an uninteresting field until the 1960s and 70s, when black holes, thanks to Hawking and Penrose, became in vogue. That community switched to nuclear physics. They wanted to understand the implications of the Big Bang model for the formation of elements and stellar evolution. And so it was nuclear physicists who took over. And Lemaître was not interested in that. It was not his field. And by the time he came back into the scientific community when Belgium opened again, this was already past him. And so he worked on many other interesting problems, but not these problems. And it was not because of his religious life. It was because of the situation in Europe. Remember that Einstein escaped from Europe before the Nazis essentially closed it down. So it's, that's one reason why he's forgotten. I'm not going to talk about Stigler's law of eponymy, but you can ask me about it. It's very interesting. It's that the law that no law is named after its originator. It doesn't actually work all the time, but it's an interesting one. Lemaître clearly was of prime importance in demonstrating that the physical universe expanded from a very different state. And Jim Peebles, the cosmologist, in a preface to a biography of Lemaître, makes the extraordinary claim that that demonstration grew out of advances in the 1920s and 30s that to a striking degree were the work of a single person, Georges Lemaître. And Luminette points out when he was discussing Lemaître's contributions actually to dark energy, he says it was not that simple in front of an audience that was 3/4 Anglo-American, for whom the history of modern cosmology reduces to the single name of Hubble, to explain that Lemaître, in French and 40 years ahead of time, had already given all the ins and outs of the cosmological constant. And so, bottom line is that this resolution that was introduced before the International Astronomical Union to recommend, because none of these are binding, that Hubble's law be referred to as the Hubble-Lemaître law, actually passed by electronic vote, which was announced on Monday, 78% in favor, 20% against. There are a few astronomers here who have objected to it, but it was very much in favor. And so I would encourage those of you who do astronomy or talk about it to refer to the Hubble-Lemaître law. The constant has not been renamed. That's Hubble's constant. It's just the Hubble-Lemaître law. And I want to close by pointing out then that Lemaître led a largely harmonious life, except for that time in World War II. And the harmony was not only in his science, but also in his religious life. And he could bring the two together in many ways, not only in the example I gave from the Nature paper, but in 1934, accepting the Franck Prize, he said, "Science is beautiful. It deserves to be loved for itself, as it is a reflection of God's creative thought." And I don't know many people who can express that kind of viewpoint in so beautiful and succinct a way. And so I'm very glad that Georges-Henri Lemaître has now, at least through the International Astronomical Union, been recognized through the Hubble-Lemaître law. Thank you very much. Well, you've just articulated my view, and I think that was essentially what Lemaître was saying, and that certainly is the Thomistic point of view. And I think one of the difficulties that we have is sometimes scientists have not thought this through, and as I said, think of God as a kind of a super creature in time who is able to make things. And because, we don't really have much education in philosophy and theology and religion anymore in general, people buy it. That's the problem. So, well, first of all, I would modify slightly what you said to accommodate how I see things. God is not separate from the universe, but God transcends the universe. God is transcendent and immanent at the same time. The question of how does it work, how do you get something from nothing, is by definition, Lemaître talks about this, outside of doing physics in the universe itself. And so I don't think it's amenable to science. And I would point out that actually this is not just the point of view of, let's say, a Catholic scientist. I'm trying to remember now the names of the authors. The Singular Universe and the Reality of Time was written by an astronomer and a philosopher, neither of whom are believers, and they have made the point that trying to describe the creation of the universe, or the beginning of the universe, or let's say the creation of the universe, something from nothing, by applying physics actually makes no sense, because you always have to have boundary conditions to the problem that are within the purview of the physical laws that you're applying to the problem. And by definition, if you're trying to explain how something comes from absolutely nothing, not a vacuum energy or quantum fluctuation, but something from absolutely nothing, there is just no way to apply physics to that. It has to be either a philosophical statement or a statement of faith. One or the other. It's not a statement of science. And, I think one just has to really accept that, that it's beyond the purview of experimental science. Which is why I think that the statement that Hawking and Mladenov made, that philosophy is dead, is not right. Philosophy deals with the metaphysics of reality that cannot be approached by science. And you're absolutely right. Aquinas talked about all of this at great length and with great power, but he did it from a philosophical point of view. And we just have to, I think, resist the temptation of imagining that we're at the point where we can make a sort of a physical model of how that happens. Yes, in terms of, not all academic departments of philosophy. I can't speak for Chicago. I have some familiarity with Notre Dame. But to a large extent, it's certainly been diminished, let's put it that way. And I think, as much as my passion in my career as a scientist, I've devoted my life to that. But I think it's important, and I always try to remind myself, that science is a practice. And in fact, the biologist Jerry Coyne, who's an atheist, said something that I think makes a tremendous amount of sense, which is that science is really just an extreme example of common sense. It's the application of common sense. But to use that, you have to be aware of and willing to accept its limitations. And to say that science, either alternatively, that science can explain everything, or alternatively, that things that are not testable by science just simply don't exist, is simply going beyond the warrant of the scientific approach. And, beyond that, I can't say much more. I do bemoan the diminishment of philosophy in the academia of the Western world. I agree with you. When Lemaître did that work, he did it as sort of a set of toy models, the Phoenix universes. But he also did something very interesting at the time, which I didn't have a chance to talk about, so thank you for raising it, which is the cosmological constant. So Lemaître was someone who was always engaged with the data. I mean, he was a theoretical physicist, mathematician, but he was always engaged in the data. And when he had worked out his modified de Sitter model and published the Big Bang, he realized that the time scale of the universe, time back to the Big Bang, was actually shorter with the derived constant that he and Hubble had both derived, both of them, that the time scale of the universe, the age of the universe, was shorter than the age of the Earth. I mean, he read papers from geologists who were determining the age of the Earth. And he realized it was a problem to have a universe that was actually younger than the Earth. So he began to fiddle with cosmological constants. And so he had this model, which is shown here, in which he has three phases, and he allows the cosmological constant to come into play. So he has a very steep expansion phase, followed by stagnation, and then a second expansion stage. And by doing this, he has been forced to introduce this fudge factor, which is actually time-dependent, but it allowed him to stretch out the age of the universe, so it was consistent with that of the Earth. Now, later on, better determinations of the Hubble constant, mostly from better determinations of distance, brought the constant down, which makes the age of the universe longer. But what's interesting about this is that it was the starting point for a couple of papers that he wrote in which he speculated that the cosmological constant was not a geometrical term. It was not some fudge factor in the geometry of space. That it was actually a vacuum energy. That space had this negative pressure that would tend to push things outward. And he actually wrote this down in the equations. He moved the cosmological constant from the left side of the equations of relativity, with the geometric side, to the right-hand side where he had the matter-energy tensor, and he called it a vacuum energy. And Kirchner has pointed out that this was, in the 1930s, an extremely advanced precursor to the notion that there is dark energy that is accelerating the universe. He didn't have the data to realize that. That didn't come till the 90s. But he anticipated it by considering the cosmological constant as a vacuum energy, which was quite remarkable. Okay, well, I think the question you've asked constitutes a koan in Buddhism, which is, if there's a big bang and no one's around to hear it, does it actually make a noise? And I don't know. But to be more serious about this, Lemaître always called his model the primeval atom model. And he regarded it from the point of view of this sort of low temperature splitting of this initial concentration of everything into one quantum. That was wrong. We know that that was wrong. But he had, this was before nuclear physics. So the modification, which is that this initial singularity, first of all, we have inflations. There's this rapid period of inflation, and then we have the expansion we know today, involve very high temperatures. And so in some ways, it is more accurate to call it a Big Bang. Actually, Hoyle, I think when he first said this, called it, he said either a big boom or a big bang, so you can take your pick. In a sense, that's more accurate. It's just a name, so I'm not sure it's sacrilegious necessarily, but yeah, and then there's the big crunch. It's a name that is so deeply embedded in our culture now that I don't really know what to say about it. I don't think it'll ever change. But it's interesting that someone who is deeply opposed to that model would end up giving it the name by which we know it today. And in part it's because Hoyle was so well known and was such a famous personality. But in many ways, it fits what actually happened, I have to say, better than Lemaître's name for it. Yeah.
Well, that was...
You're going to throw me out.
I am.
Okay.
We'll cut
That's
you
all
off.
right. Fair enough. All right.
But it was wonderful.
Thank you.
In the proper sense of the word.
Great. Thank you.